Ladies and gents, gather round. I've got tales of AI to astound. As my keynote will make clear, I'll boost your profits this year. And then later, we can all have a beer. That was brought to you by ChatGPT. Thank you very much. This talk was entirely written by ChatGPT. I'll just be reading the lines that it told me to read. Everyone get in line. I was told to put a slide up front of my credentials, so here you are. So I'm the chief data scientist at a company called Nebula. You can see me in the back right corner there with my puppy Obo. And Mike is here as well, Mike Evers. He's in the the back row on the far left. I wrote Deep Learning Illustrated, as Amber mentioned, which was a #1 bestseller in AI. I host a Super Data Science podcast, the most listened to podcast in the data science industry. I lecture at places like Columbia, NYU, and I lecture a lot in the O'Reilly Learning Platform. So, now you know who I am. Why am I here in front of you? I've been invited to give this keynote today to detail how you can derive commercial value from AI and to contextualize the capabilities that AI can deliver for you as you make your way through the other talks over the course of today. Why does AI matter to you? Each passing year, AI adoption becomes increasingly critical to your business, but things are only just getting started, and here's why. This is Jeanne Calment. She was born in France in 1875. When she was 1 year old, the telephone was patented. When she was 4, the light bulb was patented. The steam turbine was invented when she was 9. Oh, also, all of these images are AI generated. So all the images above the pink line will be generated by an algorithm called DALL-E 2, which I'll be talking about more later. Steam turbine was invented when she was 9. Wireless communication with radio waves when she was 20. The Zeppelin as well as fixed-wing flight were both invented in her 20s, except for general anesthesia. All modern medicine was developed after Jeanne's birth. X-rays were discovered in her 20s. The term gene was coined in her 30s, and penicillin's antibiotic properties were discovered in her 50s. So up until then, you could die from a very simple cut from an infection. In terms of information technology, the first programmable computer, the Z1, was devised in her 60s. The transistor that was subsequently invented that allowed machines to shrink was invented in her 70s, email in her 90s, and at the time of her 100th birthday in 1975, DARPA devised the basis of the modern internet. And yes, Jeanne was a lifelong smoker. This illustration is derived from a real photo of her at her 100th birthday. So Jeanne passed away, despite her smoking habit, in 1997, 122 years young, making her the oldest person whose age has been verified by official documents. The change that Jeanne witnessed in her lifetime was spectacular, and that dramatic technological progress corresponds with dramatic, quantifiable improvements in the quality of life on Earth. So for example, 2 centuries ago, the vast majority of people on Earth regularly went hungry every day. Today, fewer than 1 in 10 are in extreme poverty. 2 centuries ago, a small portion of adults on the planet could read. Today, the vast majority of people on the planet can read. And 2 centuries ago, nearly half of all children died before reaching the age of 5. Today, worldwide, only a few % die before the age of 5. And correspondingly, life expectancy when Jeanne was born was just 38 years old. By the time she died, life expectancy had more than doubled to 77. Given this lifespan progress and how it has continued to extend in recent decades, it feels safe to assume that of the more than 100 million babies that will be born this year, 1 will live as long as Jeanne Calment did. What changes will this child bear witness to? Can we even imagine? Just as a young Jeanne Calment probably couldn't have imagined mobile phones and laptop computers and nuclear energy, so too are we probably incapable of predicting the technologies that will be dominant a century from now and what they could mean for the quality of life on Earth. Indeed, while Jeanne Calment might have been able to make predictions a few years out, maybe a decade out, because of the pace of technological progress at that time, certainly could not have predicted, a century out, as I was just making the case on the last slide. Today, even making predictions a few years out is getting harder and harder and harder. And this is due to a confluence of factors, such as more human brains on the planet than ever before. And the human brains that are on the planet have more time available for cognitive tasks than ever before, than, say, tilling the fields. And those human brains, with all of their extra time, all of their cognitive time now, many of them are connected in real time over the internet. So a new discovery, an academic journal article, or a piece of open source software can be shared instantly to all of those brains that are doing all of that thinking. So thanks to these opportunities for inventiveness and problem solving, the rate of technological progress is much more rapid today than ever before. But of all of the human capacity for intelligence on the planet, there is another factor that interacts with that is multiplicative with human intelligence. That means technology is moving at an exponential pace. And that, of course, is artificial intelligence. So effective AI models are typically fueled by data. And the number of data collecting sensors on the planet is expanding rapidly. So mobile phones, self-driving cars, digital assistants, industrial sensors, and so on, they're all collecting more data at a higher resolution than ever before. And since AI models need data to be trained, well, we got plenty of that in abundance. And conveniently, storing all of these abundant data is getting exponentially cheaper each year that goes on, as does the cost of the computing to crunch all of those data and train powerful AI systems. So, while AI developments in the coming years will be so rapid and so paradigm shifting that the exact timeline and specifics of it are unknowable. Hello, welcome. Over the next 45 minutes, I'll be detailing how you can nevertheless harness AI today to drive significant commercial value. While you're listening over the next 45 minutes, I'd like you to reflect on how the value-enhancing AI applications I describe relate to your business. Then, in the final 15 minutes, you'll have time to ask me whatever questions you like. So to provide you with food for reflection on specific AI applications that are relevant to you, I'll cover what deep learning is and how it's driving the AI revolution, examples of work that are replaceable with more affordable AI versus examples of work that can be augmented and done more efficiently with AI, and then I will leave you with concrete tips on how to implement AI projects successfully yourself. These topics are important to you because successful adoption of AI will drive efficiencies in your businesses, and those increased efficiencies will allow you to exit at higher valuations. So first, we're going to talk about deep learning, the specific approach that has been driving the vast majority of AI innovation in the past decade and that will continue to accelerate technological progress for the foreseeable future. To effectively introduce deep learning, let's start with what AI is. Well, it's a buzzword, isn't it? It doesn't really mean much at all. It's a kind of term that the popular press uses in order to describe upcoming technological capabilities. So what was AI in the 90s seems to be something different than it is today, so there's kind of moving goalposts on that. But within the field of AI, there are specific fields that we can concretely define. So in the 90s, a very popular AI approach was something called expert systems, where programmers worked with experts in order to hard code how a machine would respond based on particular inputs. So IBM's Deep Blue computer that defeated Garry Kasparov, this relied on software programmers working with expert chess players, and then they figured out, okay, let's put an if statement here, a for loop here, and eventually we'll have enough programmers working enough that we can defeat Garry Kasparov with an enormous amount of human ingenuity. The dominant AI approach today works completely differently, and that's machine learning. So with machine learning, instead of programming, hard coding in how a machine should respond based on particular inputs that come in. With machine learning, instead, we allow the algorithm to train on data, typically lots and lots of data. And so that's what figures out what output should come out based on a particular input. Historically, when we were developing machine learning models, in order for them to work effectively, we had to do something called feature engineering. So up here on this slide, I have examples of two very famous features for the first real-time face detection algorithm. So these features allowed an algorithm in your phone, or actually at that time in your camera. Around 2006, this algorithm appeared in cameras to automatically detect where faces are and then adjust the focus. In order to allow that to happen, big teams of PhDs and postdocs and professors would work together to come up with the most clever features to detect a face. So in the middle panels there's a feature that detects the darkness of the eyes with the relative brightness of the cheeks underneath. This one over here detects the brightness of the nose with the darkness of the eyes on either side. So these are examples of features that had to be engineered. You had to be an expert in detecting faces to build a machine learning algorithm that could recognize faces. So most of your time as a machine learning practitioner historically was spent on engineering features, being expert in your data. Very little time was spent on actually training your models. With deep learning, this has been turned on its head. With deep learning, you might spend little or in many cases none of your time engineering features from the data. Instead, you spend your time coming up with deep learning model architectures and training your models. And then you rely on the models to automatically extract these features from the data. And so I'm going to go into some more details on specifically how this works in the upcoming slides. But to give you just a little taste here, this is from a very famous machine vision algorithm from just a couple of years ago. And instead of having these human programmed features put in, there's one artificial neuron, which is an algorithm that is designed to loosely mimic the way that a biological neuron, a biological brain cell, works. So the deep learning network, the artificial neural network, has many layers of artificial neurons. And at this particular layer here, which is relatively deep in the architecture, you have all of these different artificial neurons that can be learning different things based on your training data. And this neuron right here has become specialized to detect faces. So you can see as this man and this other man comes into frame, this particular neuron lights up and is able to detect them. So with deep learning, you no longer need to be an expert in detecting faces to have an algorithm that can detect faces. All you need is training data of faces. And so that means that this deep learning algorithm, not only can it recognize faces, it can recognize thousands or potentially millions of other kinds of objects, just depending on how big you make the network and how many training data you have. So with deep learning, we can now, without a PhD, implement near state-of-the-art algorithms without being expert in any of the kinds of data that you're working with. All you need is lots of great data. And it saves a lot of human time because now we can just create a model, leave it running for a day, maybe a couple weeks if it's a really big model, and we don't have to spend all this time engineering features. And on top of those advantages, it's much more nuanced and much more accurate. So this nuance facilitated by deep learning what has allowed you in so many consumer and business applications to have what feel like magical experiences. So things like voice recognition, translation between languages, image generation, and yes, ChatGPT. All of these kinds of things just a few years ago were error prone and felt clunky because people were trying to do it this human feature engineered way, and now we don't have to worry about that. So any kind of approach, any kind of machine learning approach that aims to learn these features from the training data automatically, we call that representation learning. Within the field of representation learning, effectively the only technique to be doing it today, the only one that's really used, is deep learning, which we can also call artificial neural networks. So how do these systems work? So you kind of have a sense of the magic and power of deep learning. Well, deep learning is inspired by the way that your biological brain works. So when you look at something, let's say you're looking at a mouse, all of that raw light information flows from your eyes to the back of your brain. And in the back of your brain, the first layer of brain cells that processes that information can detect straight lines, and that's it. So you have thousands of cells that just detect lines at different orientations. And then a second layer of cells can receive that straight line information and recombine it into corners and curves. And then a third layer can take those corners and curves and have increasingly complex, increasingly abstract representations created from those corners and curves. And then as we go many layers deeper, through increasing complexity, increasing abstraction, your brain allows you to perceive complex objects like a bird or a cat or a dog or what have you, all of the individual faces in this room. So, while it must be really cool to be spending time with a guy like me who enjoys reading about this kind of thing on a Saturday afternoon, this neuroscience is useful to you commercially because we've figured out how to mimic this same kind of hierarchical learning in machines, and that is deep learning. Let me show you how it works. This is a tool that you can use yourself. It's at playground.tensorflow.org, and it allows you to build deep learning networks just in your browser and see how they train. So if we want to solve a very simple problem, like this one here, where we're trying to distinguish these orange dots from this clump of blue dots, we can solve this problem with an extremely simple artificial neural network. So all we need is one artificial neuron, one of those artificial brain cells, in one layer, and it splits the orange from the blue very easily, and perfect. So simple problem solved. As we make the problems more complex, like separating this orange ring from the blue dot in the middle, if we leave our artificial neural network super simple, the best that it can do is fit a line somewhere. And so these oranges are classified correctly, these blues are correct, but all of these oranges here are misclassified. So we can just add a little bit of complexity to our network. We can add a couple more artificial neurons into the single hidden layer. And now we can place 3 different straight lines at different orientations. And those 3 straight lines can be recombined to create this hexagon. And now we can very effectively distinguish the blue dots from the orange dots. And as we go to increasingly complex problems, like this spiral problem here, we won't be able to do that with this now relatively simple artificial neural network, but we can just add in more hidden layers. So as soon as you have 3 hidden layers or more in your artificial neural network, that is a deep neural network or a deep learning model. So while AI may be a buzzy, vague word, what deep learning is extremely specific and extremely concrete. And now if you didn't know what it was before, you do. And so with this kind of architecture, if I add in 4 layers of artificial neurons, crank up the number of artificial neurons in the first few layers, with this kind of architecture, I can solve the spiral problem. But instead of watching that train as we sit here, I actually already have this completed running back in my slides. So here we have the whole neural network having learned, and you can see, just like in our biological brain, the first layer is able to detect straight lines and straight lines only. The second layer can recombine those straight lines into curves and corners. The next layer can take those curves and corners and make increasingly complex, increasingly abstract shapes, until by the 4th level, the level of complexity that can be encoded within this system is very similar to the spiral shape that we were trying to learn. So that's how deep learning works. There are 3 big categories of problems that deep learning has so far proved to be extremely effective at. The first is machine vision. I love machine vision because you can so visually see how deep learning is so powerful. So with machine vision and deep learning, you can have algorithms that detect where objects are in an image and then can very accurately classify what those objects are. Or you can do something called image segmentation, where every pixel in the image is classified as a particular kind of object. So in this case, humans in red, road in purple, trees in green, sky in blue. So you can imagine how effective a system like this is for, say, a self-driving car. If we tried to use the old school manual feature engineering approach that dominated machine learning for years, this would be impossible. There's just too many possible permutations to be able to detect what a horse is or a human is or a car is. But with deep learning, all of this nuance can be learned automatically by our deep learning architecture and be extremely accurate. So just to recap, this is deep learning, and this hierarchical learning that we have with deep learning is inspired by the way that biological brains process information hierarchically with increasing complexity as we go deeper into the hierarchy, which enables the staggering nuance of being able to, say, detect faces like this algorithm can here, this deep learning architecture, and that enables these kinds of almost magical machine capabilities. In addition to machine vision, there are other machine capabilities that are now possible thanks to the nuance and accuracy of deep learning. Deep reinforcement learning is a very exciting one. Deep reinforcement learning allows algorithms to make a series of decisions in very complex environments. So for example, Go is a game that is hugely more complicated than chess. Up until a couple of years ago, it was assumed that it would be decades before a machine could beat the world's best Go player. And yet, right here in London, the Google DeepMind team did exactly that using deep learning, that incredible nuance capability learning of deep learning. Same kind of thing for complex strategy games like StarCraft. Machines, thanks to deep learning, are better than humans. And it isn't just games. We can also have real-world applications, like a robotic arm can solve a Rubik's Cube if you put a camera with it. And same kind of thing, just lots of training data with deep learning, and it figures out how to solve this. Even humanoid robots like Boston Dynamics are powered by this kind of approach. So that's machine vision, deep reinforcement learning, but of all of the application areas that deep learning is supercharging, the one that I'm most excited about and that I'll spend the most time on today is natural language processing. Particularly something called transformer architectures that have emerged just in the last couple of years that power tools like ChatGPT. These transformer architectures allow these natural language processing algorithms, natural language just meaning like the sound of my voice going into your ears or words written on a page. Any of this natural language can be processed by machines, and these transformer architectures are capable of contextualizing information over very large stretches of language, as you've experienced if you've carried on a long conversation with ChatGPT. So these transformer-powered architectures, a number of companies have released models in recent years that have enormous numbers of what we call model parameters. So those artificial neurons that I was showing you earlier in that interactive demo, instead of just having one or three or a couple dozen like the ones that I designed for you, these transformer architectures in these foundation models have at least hundreds of billions of those artificial neurons. Increasingly, they have trillions, and that enables these transformer architecture foundation models to have incredible capabilities. DALL-E 2, for example, can create images, high-resolution images, based on whatever natural language you type to it. I'd like to see an astronaut on a horse. Well, now you have it, and lots of examples. I'd like to see the astronaut on the horse in this style. And now you have it, lots of examples. And so that's how I created all of the inventions in Jon Krohn's lifetime on one of my opening slides. I was using DALL-E 2. Similarly, last year, Google released an algorithm that does the same kind of thing with video. So at this time, just a few seconds of video, but you request to the Google Imagine or Imagen video algorithm what you would like the video to have in it. So in this case, a book with the words imagine growing out of it, and boom, you have it. This is incredible. And ChatGPT being yet another example of this kind of technology. So huge teams of linguistics and art PhDs and postdocs could never dream of engineering features to produce these mind-boggling models. Only thanks to the extremely nuanced automatic feature learning capabilities of deep learning is this possible. Okay, so transformer-powered foundation models are clearly really cool. Many of you in the room have probably played around with several of these. But why should you care about these commercially? Well, that is the second part of my talk. So you should care about AI commercially because it replaces some types of tasks that humans do, and it augments and improves other types of tasks that humans do. In this second section, I'll guide you through specific examples of replaceable and augmentable tasks, but in either case, the key points are that thanks to deep learning, machines drive commercial efficiencies by doing tasks more quickly, routinely millions of times more quickly than a human could, doing tasks more cheaply than humans can, and again, thanks to the highly nuanced, automated feature learning of deep learning, it can also do it more accurately. So, repetitive tasks that people do are the most prone to being replaced. So things like customer service, data entry, bookkeeping, proofreading, manufacturing, and retail sales, all of these areas have highly repetitive tasks that can be replaced by machines that are faster, cheaper, and, again, thanks to deep learning, often more accurate than humans at these tasks, saving your business money while improving customer experience to generate more revenue. On this slide, as well as the next slide, I'll go into B2B SaaS specific examples of ways that you can replace tasks with AI, repetitive tasks. So this particular slide is all about my favorite, natural language processing. So going back to the foundation models that we were talking about with those hundreds of billions or trillions of parameters, those are capable of impressive general capability. So you can, soon there will be a ChatGPT API that you can call. That's expected in the coming month or so. In the meantime, there is the same company, OpenAI, offers their GPT-3 API that has a lot of the same general capabilities of ChatGPT. And Google is working on an algorithm called Apprentice Bard that is expected to compete with ChatGPT and might be released in the coming weeks. And so all of those kinds of algorithms, you can pass in, as you've probably experienced with ChatGPT, a huge range of possible kinds of natural language requests, and therefore can help you in a very broad range of general problems generating text for you. Separately, with natural language processing, instead of having these big general foundation models, you can also have highly verticalized specific natural language processing models to your niche that are customized to you, and the intellectual property can be owned by your business. There are tools out there that allow you to do that more efficiently. So for example, Google Dialogflow, which was introduced to me by Mike up here, it allows for the automation of customer service tasks in particular. So Mike was involved in the development of a chatbot called Carrie when he was working at a company called Harry. Yes, they decided at some point to call it Harry Carey. And that chatbot is capable of automating lots of HR tasks like onboarding new employees for high-volume restaurant roles. So for that highly verticalized segment, you now have a chatbot that can handle all of the kinds of regular orientation and feedback that are provided to new hires. So that's natural language processing. Beyond natural language processing, there are two categories of replaceable tasks with AI that I think about. So those two big categories, the first one is kind of technical and business-facing tasks. So these are where your internal employees are using tools and getting information from AI. So previously, tasks that would have to be done by a human, like say data analysis, predictive analytics, that kind of thing can now largely be automated, which frees up those data analyst resources for thinking up insights or commercial opportunities instead of getting into the low-level coding and analysis themselves. So internal technical interfaces are one category of applications. The second are less technical, more intuitive applications that your users interact with. So this includes things like automated personalization. So you can personalize the customer experience with AI by, say, recommending products or services, the whole feel of your platform based on specific user behaviors within your platform or maybe on the broader internet. So hopefully those are some interesting examples and categories of tasks that you can automate completely, repetitive tasks that you can automate completely in the B2B SaaS space. Now I'll move on to the kinds of tasks that can be augmented with AI. So tasks that can be augmented with AI, they tend to be much less repetitive. So that's the clear distinction. Highly repetitive, automatable with AI, not repetitive, can be augmented with AI. So tasks that require creativity, leadership, and decision-making, for example, these can be augmented with AI. And ChatGPT is my favorite tool today, of course, for doing that kind of thing. So you can use ChatGPT to ideate and draft copy for contracts, business plans, pitch decks, emails, marketing materials, social media posts. I may even have used it genuinely for this talk today. I can bring it up right here in ChatGPT to make sure I was rounding out with lots of different examples. In this talk, I asked ChatGPT, what are ways that B2B SaaS companies can leverage artificial intelligence for commercial value? And some of the examples that I just gave on the last few slides, like predictive analytics and personalization, were cued by ChatGPT, so thank you. And of course, also my great opening poem. So, super powerful tool. You can also use it to summarize articles, so you can pass in URLs, and it can summarize web pages down to a small number of words, which can even include, you could say, shorten this document for me and use simpler language. So you could pass in some crazy new AI article with lots of technical jargon, and it can figure out how to distill that down into simpler terms for you automatically and augment your intelligence. You can also use it to plan and suggest solutions to very specific problems that are specific to your business. How do I increase revenue or profitability in this very specific circumstance that I'm encountering? Describe it to the algorithm. How can I retain customers better in this specific circumstance? What product features should I consider building next, given these product features that I already have? Or what AI products could I be building, given my particular data, my industry, and other defensible moats that I have in my business? And if none of those questions work, you can at least use ChatGPT for motivation or even therapy. So beyond ChatGPT, there are other great transformer architecture powered deep learning algorithms, foundational models that can do other incredible kinds of things. So if you're a software developer or you have software developers in your company, which probably everyone here does, the OpenAI Codex API is crazy for allowing you to provide natural language instructions that create code and allow you to, for example, in 7 minutes in this demo video, the user creates just by passing in natural language processing, like display some text that says firing thrusters in white, and whatever that level specificity over the course of 7 minutes, they created this video game in the browser that involves a spaceship chasing away from an asteroid. It's crazy. And of course, we've all been augmenting our intelligence for years already, prior to these foundational models, with things like Google searches. And today, those Google searches, and yesterday Microsoft just announced that their Bing algorithm, apparently as of today, incorporates ChatGPT. And so instead of just typing in the words related to some document that you're looking for, you can, a la ChatGPT, ask extremely specific questions, and it'll understand that context and bring back to you natural language results. So the way that we're using search engines is rapidly increasing today, and you're still going to want to be doing a Google search to confirm that information that you get from an algorithm like ChatGPT is correct, because a flaw of these algorithms today, in case you aren't already aware of it, is that these algorithms will lie to you very confidently and persuasively. So if you're making a very big business decision based on some information that ChatGPT has given you, you might want to double check with some experts online before you move ahead with that strategy. So augmentation with AI is, for me personally, the place that I'm most excited about in B2B SaaS and where I see the most opportunity, and that's where our company Nebula is making lots of strides. So to give you a concrete example, with our Nebula platform, you can use it to search for people. So we scrape the open web for all the information that we can find on people, and then we use that publicly available information to allow you to find people. It could be talent that you're looking to hire or a particular sales lead, and all of our competitors' tools use keywords, which are extremely clunky, extremely restrictive, and so instead, now today, you can pass in natural language, so I can grab a few relevant bullets from my LinkedIn profile and paste these in here and say that I'm looking for a chief data scientist. And then our algorithm can consider all of that natural language holistically, understand the meaning of this, and bring back relevant profiles that might not have any of the same words, but we get these people that have a similar meaning to me. And so one of our early clients was one of the world's biggest microchip companies, and they did an internal study finding that 12 times more of the best candidates were found using this kind of natural language deep learning approach that we provided them with relative to their keyword-based approach. So hugely powerful, 12 times more of the relevant candidates they were missing in their own talent pools when they were searching over them. 90% of the great people they were missing because they were using clunky old keywords instead of deep learning AI. And this kind of thing, you can do this in your verticals as well. So whether it's legal documents or what have you, you can be using natural language processing and deep learning to have very nuanced, very powerful search. We can also be using these foundation models to augment aspects of the platform, like automatically generating relevant images or videos for our users. A particular exciting thing that we have on our immediate product roadmap is allowing these searches to be automatically extended. So I could provide just a little bit of text. I could have just said, Chief Data Scientist, and I'm not sure how else I want to flesh out that query. We can use a foundation model out of the box, like GPT-3, pass that language to GPT-3 and say, give me some resume bullet points that are relevant to Chief Data Scientist, and then for our users, they just in seconds, instantly, have bullets appearing. Some of those will be highly relevant. They'll say, okay, I'll keep those, and others they can get rid of. So these foundation models, you can be using them too to power natural language or image generation or video generation capabilities in whatever your B2B SaaS platform is. And a really cool thing, which I debated, I think this is potentially so cutting edge that I don't know if Mike is going to kick me after this presentation, but I couldn't resist sharing this with you. Maybe when we publish this on YouTube, I'll just cut this part out. Because these foundation models can allow you to save months, years, in many cases, of data science R&D on specific models. So in our platform here, you might want to say hard filter on a particular educational institution. So you only want to search for people from Oxford University. But, well, let's expand a little. I want Oxford University and also related universities. So my data science team, we've had this as a relatively high priority for years. Let's build this model, let's train it. But every company has limited resources. As we were hearing in Talon's great talk yesterday on product road mapping, you have to be prioritizing things, and other models just keep coming up on top. So wouldn't it be nice if we didn't have to build that model at all, and it could just exist? And that all of a sudden has happened today. So here is a little demo that a data scientist on my team built. All of the back-end computation is happening with the GPT-3 API. And so we can say now, I want universities that are similar to some specific university. And so this is just a demo environment to be a proof of concept of the capabilities. But we can use these NLP foundation model APIs to generate similar universities. So in our platform, the user could type in Oxford University into this field, and we could say, would you like some related universities? And poof, Cambridge, Stanford, Harvard, these just come up. And we could do this for other fields in the platform. We have, in addition to educational institutions, you have, companies that people have worked at. So somebody's headhunting you while you work at, say, HG Capital, and you could be then having related companies pop up, and you can tell me if you think that these are relevant. But KKR, TPG, Carlyle Group, does that seem reasonable? So my team I might have had to dedicate a resource for 6 months or 12 months to developing a model that could do this. And instead, we can use the GPT-3 API, soon the ChatGPT API, out of the box to solve all these broad range of problems. So there's an enormous amount of creativity that you can have about how you can be integrating AI into your platform very quickly, thanks to these super powerful foundation models. So in this final part, hopefully I've gotten you really excited about what you can be doing in your products with AI, with how you could be replacing or augmenting tasks. And so now I'll provide you with my top tips on how to implement AI successfully. I've got 4 sections in here. The first is data, then I'll talk about my approach to modeling, to doing R&D. I'll talk about getting the right people in place and equipping them with the right tools. So data first. If you don't have data scientists yet or an AI research team, and you know that you've collected a bunch of data and it's just sitting in a data lake, it's going to be a while before that data science team can do anything with your data. So it might be a minimum of 6 months, minimum, before machine learning models can be developed based on those data, because the unstructured data like you have in a data lake, it's not going to work. We need to organize the data into columns where each column represents a different potential input into the model or an output from the model that we'd like it to be able to learn. Missing data need to be noted and handled sensibly for a given situation, and all the fields need to be consistent. You can't have one column that represents distance where in some rows it's imperial and in others it's metric. So all this kind of data cleaning and structuring is the important first piece that can be very time consuming if you haven't started on AI projects with your data before. Once you have your data in place, my recommendation is to start with very simple, completely explainable models. So there's models like regression models or semi-supervised approaches that allow you to have an extremely good understanding of how your model inputs map to some particular outputs. These models can be created quickly, and they can be used as a proof point to demonstrate that there is some signal amongst the noise in your data. It should only be after that that your data science team starts tinkering with deep learning approaches like the ones I've been talking about today, or other powerful modeling approaches like gradient-boosted trees. So because AI projects can have all this complexity, getting all the data into place, experimenting with simple models, getting into more complex models, and the resources that you have working on these problems are typically expensive. So in order to have successful AI in your company, you need to have an R&D culture that is accepting of this high-risk work. The most defensible intellectual property that you will create with your AI will inevitably be these high-risk projects. But I have a personal philosophy that allows you to balance those high-risk projects and still see results by doing high-risk projects alongside much more tractable, lower-risk projects. So you can have your data science resources splitting their time between not moonshots, but just higher risk, much more value-adding AI that's game-changing, while simultaneously working on more concrete, discrete tasks. And thanks to the kinds of foundation models that I was highlighting for our own platform just a couple of minutes ago, these kinds of lower-risk tasks are becoming easier and easier and easier for your AI teams to be developing. In addition to that kind of general philosophical approach, you're going to want to have data science team-wide lab meetings regularly. You're going to want to have tons of whiteboarding, a journal club for people to be studying the latest and greatest papers that are coming out in your company's particular niche. And I highly recommend sending your data science team resources to external conferences at least a couple of times a year so that they can talk and learn about what's going on in the space, have their eyes open to completely new kinds of things than they did before. And a tip to you personally, if you're an executive who doesn't have hands-on AI experience, is don't send your data science team every blog post that you read about AI. Executives' gut instincts on AI can be way off, and you're just kind of cluttering your data science team's day, especially if you're kind of expecting a response based on this blog post of this latest and greatest AI capability that you just read about. So What kinds of people do you need on your team in order to have a successful AI R&D culture? Well, of course, you need data scientists. And what does that mean? Well, data scientists aren't data analysts. They aren't business intelligence people. Data scientists are capable of training training models based on data. They might be training data based on models, but that's a whole other thing, synthetic data creation. Training models based on data, not just analyzing data. And especially in uncertain times like these, if you want to have business agility in these uncertain times, then those data scientists that you hire, I recommend that they be highly versatile, full stack data scientists who are capable of engineering their own data pipelines into their model. They can develop the models themselves. They can deploy those machine learning models into production themselves. And they might even be able to help you with pitching and selling to investors, prospective clients. That kind of highly versatile, full stack data scientist might be hard to find, but that is why we've built platforms like Nebula to make that kind of search easier. So in addition to data scientists, there are lots of critical roles that cannot typically be filled by a data scientist in order to ensure a successful AI product. I'm not going to read through these or just tell you them, but you can take a photo if you'd like this for posterity. Our photographer is doing just that. And again, I'll remind you the URL where my slides are at the end of this talk. Once you have your data science team in place, you need to equip them with the right tools. And so you can't hamstring them on their local machine. Your data scientists need to have free rein to install software, open source software. And they probably need to be doing that on a Mac operating system or some other Unix-based operating system. So these are examples of some of the best, most powerful open source data science products that I love. And so again, I'm not going to run through them all, but you can take a photo or you can come back to my slides later. And then beyond just individual tools, there are also lots of best practices and tools out there for ensuring that your teams are working efficiently, your data science teams are working efficiently, collaboratively, and that they have reproducible results with their models. So each bullet here is a best practice that I recommend for your data science team, and in brackets is a particular tool that I recommend that you can use to facilitate that particular process. All right, so those are my top tips for getting value from AI. The key points that I'd like you to take away are that I introduced you to the nuts and bolts of what deep learning is. Until just the past few years, and in many cases the past few months, like ChatGPT, what I've shown you today wouldn't have been possible. So you don't need to be concerned if you haven't been injecting AI into all of your commercial processes yet, but now is definitely the time to get going on it. Later, I detailed examples of B2B SaaS relevant tasks that, thanks to deep learning, can be replaced or augmented by machines with far shorter implementation times than ever before, and the tasks can be done more quickly, more cost-effectively, and more accurately, driving efficiencies for your business. And all of you are exceptionally busy people, no doubt, so maybe some of the ideas that I brought to you today will not only help your businesses, but help you with your own time and efficiency throughout the workday. In the final section, your appetite whetted for implementing as much deep learning as possible. In the final section, I provided you with a practical roadmap to implementing AI successfully so that you can waste as little time, energy, and capital as possible getting AI projects off the ground. The slides for my talk today are available on my website at jonkrohn.com/talks so that you can be sure to not miss any of these tips, and you'll be provided with access by something called Hive. And I might be posting it on my personal YouTube channel as well. And so returning to Jon Krohn from the onset of my talk, it should now be clear that even if there is uncertainty in markets in the immediate term, thoughtfully investing in AI now is a sure bet for your company long term. Speaking of long term, recall that 122 years old, Jon Krohn lived the longest of any human on record. by thinking about the applications that I've covered in my keynote this morning, and by going through the talks and workshops throughout today's agenda, perhaps you can develop plans for AI that will enable your company to thrive for more than a century, just as Jon Krohn did.
Thank you very much, Jon. Super interesting talk. I think we have time for a few questions, if there are any from the audience. One straight up at the front.
Hello.
Hello. Hi, Jon. Thanks. That was really interesting. When you talk about the artificial neurons, just sort of translate that into computing power. What does an artificial neuron sort of consist of in computing sense? Is that a processor? Is that?
Yeah. So the question is, convert the concept of an artificial neuron into kind of computing terms. So each of these individual artificial neurons, or maybe even better, I could be bringing up the playground here. So each one of these artificial neurons here is an extremely simple algorithm. So the algorithm for an artificial neuron was invented in 1950 on a machine called the perceptron, which is now at the Smithsonian Museum in Washington, D.C. And that perceptron had, I don't know the exact number, but a few dozen of these artificial neurons. So the compute required for an individual artificial neuron is extremely small. There's very simple operations that happen in there, linear algebra operations involving simple multiplication and summing over products. And that linear algebra operation, because it's so simple, you can do it on graphics processing units, GPUs, and GPUs often have thousands of parallel processing cores. Each of those thousands of cores can be doing one of these simple linear algebra operations, and so it allows you to scale up. And actually another trick is that with linear algebra, you don't process each artificial neuron individually. You can actually do the whole layer of artificial neurons with one operation. So with GPUs, you can have extremely efficient processing of these artificial neural algorithms. Does that answer your question?
Yeah, it does. I was thinking, is it sort of in terms of a thread or a core or for each of these sort of neurons?
Yeah, so you can have the operation for a whole layer happening as a single linear algebra operation on a dedicated core. Yeah.
Brilliant. Thanks very much.
Hi, Jon. Thank you very much. Actually, it was very interesting. So one of the challenges, from my perspective, about deep learning is the idea of model validation and the real-time monitoring of these models over time. Do you have any experience about that? How do you think that is best handled?
Yeah, this is an extremely important part of the process. I actually had part of my talk, I wanted to cover that, but I only had 45 minutes up here and something had to be cut out. But this is extremely important. So when your data science team develops a model and then deploys it into production, the real world changes. So if you put a natural language model into production in 2019, there might have been very few examples of the word COVID that it had to learn with. But then in 2020, all of a sudden that word becomes really important across basically every vertical. And so your natural language model needs to be updated. So this is an example of what we call feature drift, where your model is staying the same in production, but the structure of the data, the patterns that are flowing into the model are changing over time because the real world is changing. So this is a really important area to ensure that your engineering teams have safeguards in place that are monitoring data quality in real time. There are lots of great products out there that do this. There are several Silicon Valley startups that I'm aware of that tackle this kind of problem. Monte Carlo is one particularly well-funded one.
Thank you. I understand that one of the limitations of these new technologies, these new transformation models, is that they use a tremendous amount of compute resource. Is that a fundamental limitation, or is that just the fact that the algorithms haven't been optimized yet?
Yes, so this is an extremely interesting question. So if I go back to some of the examples of these super powerful, so it was on this slide that I began introducing the idea of these very large foundation models that have at least hundreds of billions of these. So while we were talking, this artificial neural network has 24 artificial neurons, while ChatGPT has hundreds of billions of these artificial neurons. So training these models requires millions and millions of dollars of compute to train. Even running them in production is extremely expensive. If you want to run GPT-3 yourself, as opposed to using the GPT-3 API, well, one, you can't actually access the code, the model weights for the proper GPT-3, but there are open source GPT-3 implementations that you can. If you take one of those open source implementations and you're saying, I'm going to save some money by implementing this in production myself. I'm not talking about training the model in any way, just using one of these pre-trained models yourself. You think, I don't want to be paying for all the API calls. For having one instance of that running, and you're never going to just have one instance running, because your developers are going to need test environments, development environments, so you're talking like at least 3 instances just to have one available in production that can't be scaled up. Each one of those instances will require $75,000 worth of GPU hardware to run. So the costs very quickly add up. They balloon enormously if you want to be using your own infrastructure to run these enormous foundational models. So cost is a huge concern, and it will, over the coming years, it will become an even bigger concern. GPT-4 that might be released in the next few months, the GPT-3 release was, the major release was 2 years ago. So GPT-4 is expected to be in the next few months. And it is expected to be not hundreds of billions, but hundreds of trillions of model parameters, 1,000 times larger. And with it will come even more magical, even more mind-blowing capabilities. It will be a huge jump, but at an enormous cost of training and production deployment. And so the number of companies that have the capital to be producing these enormous foundation models is becoming a smaller and smaller group. So the power of these models is concentrating to a very small group. That is certainly one concern. And because essentially, like I talked about on this slide here about transformer architectures being the thing that's really enabling these natural language processing models to be so powerful, these huge models with hundreds of billions or later hundreds of trillions, there aren't actually, in terms of data science, new innovations incorporated into those. There are complexities around all of the dealing with the enormous amount of data and all of these GPUs that are training. There's like engineering challenges, but the data science is the same. We just take the same idea, we just take these transformers and we have some more of them and we add some more data. So all of this enormous success in the last few years is being driven by this extremely simple idea of let's just add orders of magnitude more models, orders of magnitude more parameters to this same kind of model structure, and let's see what happens. Thankfully, there are research groups that are aware of this kind of issue. So one of the most recent episodes of my podcast is on an approach called sparse GPT. So we need to go all episodes. So my very most recent solo episode that came out on Friday is about this algorithm called sparse GPT, which halves the number of model parameters in a GPT-style architecture like GPT-3 or ChatGPT, and it removes half of the model parameters without any reduction in accuracy. The authors estimate, they're from a German university, I can't remember which, but they estimate that based on some improvement efficiencies and other approaches, that they could remove 90% in a future paper without impacting accuracy. So there are groups that are concerned with trying to make the footprint smaller. And that's going to be essential for this stuff to be sustainable. And at some point, somebody is going to come up with some approach. We don't know what it is, but somebody in some lab somewhere is working on the next deep learning. And whatever that approach is, it will probably be more computationally efficient than the deep learning that dominates today. Great question.
Ethics and bias.
Ethics and bias. What do you mean?
Everyone, when you talk about kind of the evolution of these types of things and the self-generative aspect, kind of sits there and gets that concern about, am I going to do something wrong? Is it going to go against the grain of policy, procedure?
Mm-hmm.
Can you just talk about
For sure.
some of the areas and options that you've considered? And
For sure. So ethics and bias, super important. So I gave you a demo of our Nebula platform and how it takes natural language data and suggests people back to you based on the natural language that you put in. Now, working in this space, finding talent for your company, finding sales leads, we need to be certain that this is happening in a way that particular socio-demographic groups are not receiving some advantage over others. And so we actually spend, in terms of our R&D time on this model, more time is spent on ensuring that it works in an unbiased way than that it just produces accurate results. And so we, for example, we just had a patent approved. It hasn't been officially published yet, but in December we had a US patent officially approved for our approach to doing this without socio-demographic biases being incorporated into the model. And so there's a lot of literature out there on how you can be developing models without incorporating bias. So there are tools like explainable AI tools that can be used. So there's one called LIME. There's another called SHAP, S-H-A-P, that uses something called Shapley values to do this. And so either of these approaches, LIME or SHAP, are open source tools that allow you to have some sense of how when your inputs change, those impact the outputs. And so this allows you to develop models where you can remove things, training data, or particular aspects of your modeling approach that are introducing ethical issues. But a critical thing that we cover in our patent and that I always mention is that you need to have validation data that ensures that even if you think you've followed all of these best practices as you train your model to avoid it having ethical issues, you need to be certain after you've trained it to say, okay, with this same query, with the same input, with person from socio-demographic group A or socio-demographic group B, are my results comparable? Are they treating them equally? So you need to have validation data across different groups to ensure that this is happening, that post hoc, after you've done training, your model doesn't exhibit bias. So that's kind of like my local answer to the question on like developing models. If you're talking about like the bigger ethical issue of are machines going to take over the world and become our overlords, is that an interesting question for me to talk about for a minute? So a lot of people are concerned about this stuff. It's great that people are concerned about this stuff. A really cool outfit out of Oxford called 80,000 Hours. They are focused on helping people have the most impact that they can in their career. And the number one career that they recommend you getting into today, if you want to have the biggest long-term impact on humanity, is being an AI ethics expert. That's how big they perceive this issue to be. And there's right to be concerned. Obviously, this stuff is super powerful, and it's happening at an incredible tack. It's like we're standing at the train station, and there's this train approaching of AI capabilities, and we're kind of at this human level station. And we're watching the train approach, and it's getting faster as it's approaching the station. And possibly in our lifetimes, it'll just whip past us. And when it whips past us, we have a right to be concerned because we are really bloody awful to anything that's less intelligent than us. even, so a chimpanzee is only very marginally less intelligent than us. But we can lock it up in a cage and treat it however we like, and we don't feel all that bad about it. We have factory farming of very sentient beings like pigs, one of the most intelligent animals on the planet, and we just have them sitting, unable to move in a crate. So we have reason to believe that if something was more intelligent than us on this planet, it wouldn't treat us very nicely. And while we are only very marginally more intelligent than a pig, these machines that we're creating could be far more intelligent than us. That makes the difference between us and an insect seem like a very small gap. So reason to be concerned. However, I personally am not that concerned. We have been creating structures that are beyond any individual's control for millennia. We have been creating armies and governments that have some rules coded into them. We set them up in a way that we hope they're going to act in our favor, and sometimes things go very wrongly. The 20th century in Europe, obviously some very horrible things went wrong with armies and governments, and some smaller things still happen today. But hopefully because of all this concern in advance around AI ethics, issues will happen. Government elections in the US in 2016, AI algorithms from social media companies were hijacked to have some impact on the result of that election, but the FBI is confident that in 2020 they were able to figure that out and ensure that that wasn't an issue. So these problems crop up, and hopefully we can nip them in the bud before they become very big issues. But even if AI does become our overlord at some point in our lifetimes, between now and then, my friend, there will be great commercial opportunities.